So let's start recording, and there we go. All right, Matt, it's all yours.
Great, thank you. Thank you for the very kind introduction. It's an absolute pleasure to be speaking to you all today. So I'm going to talk on rigorous and practical computations of spectral properties of Koopman operators. So this is based on joint work with Alex Townsend at Cornell. You can find our paper on the archive. And just to whet your appetite before we get into the talk proper, these pictures show Koopman modes of a turbulent flow in dimension of 300,000 computed with robustness and error control. So you can get error bounds on these computations. Okay, so hopefully, yeah, great. So the setup for this talk is that of a discrete time dynamical system. So we have a state X that lives inside a state space omega in ambient dimension D. And the dynamical system is governed by a function f. So the time, so the state at time n+1 is given by f of the state at time n. And rather than being given f, what we're given is snapshot data. So x and y, a set of m snapshot data, so that y is equal to f of x. And the broad goal, which I'm sure we're all familiar with, is to learn the properties of the dynamical system from this snapshot data. And this is many applications. So here's a very short list. Pretty much anything that involves time evolution can be put into this framework. But I've underlined two applications that we're going to look at the end of the talk, which is fluids and molecular dynamics as well. So already with this problem, you can see that there are some immediate challenges. For example, f is typically nonlinear, unknown, and also the system could be chaotic. So you start with two initial points that are close together, and then they diverge very quickly. Okay, so I'm going to approach this problem through Koopman operators, which hopefully a lot of you are familiar with. So this goes back to two papers of Koopman and Koopman and von Neumann in the 30s. And it's a really beautiful idea. Instead of looking at the state, we look at functions of the state. So these are called observables. So functions g from omega to c. And then the Koopman operator acts on such functions by just composition with f. So this formula here. And formally, we're going to consider this operator in the L2 case. Okay, so we have some measure small omega on big omega, and then the Koopman operator acts on this infinite dimensional Hilbert space. So what we've done is we've replaced the nonlinear f here by a linear operator k, but the price to pay is that this now becomes an infinite dimensional operator. Okay, so the goal is to learn the spectral properties of k, and I'll explain why in a second. And the spectrum of k is just given by z, such that k minus z is not invertible. Okay, so why spectra? So suppose that phi lambda is an eigenfunction eigenvalue pair, then phi evaluated at time n is just given by this n-fold composition with k, and then you pull out the eigenvalue and you see that you've got this sort of nice linear response. So it behaves exactly as you'd expect. Now, because we're in infinite dimensions, not all of the spectrum of k consists of eigenfunctions. So in general, we have to consider an expansion in terms of a sum of eigenfunctions and also a continuous component. So you can do this if your system is measure preserved, for example, if it's Hamiltonian or ergodic. Okay, so these are eigenfunctions. You have a sum here, which might be infinite, and then you have a continuous component with an integral over an angle of theta, and you can view these as a continuously parametrized set of eigenfunctions. And this exactly gives you the Koopman mode decomposition. Okay, so g of x at n at time n is equal to the n-fold composition again, and you can see how the Koopman operator acts on each of these separate components. So you have a eigenvalue component, and then you have this thing here, this continuous component, which looks a bit like a Fourier series or a Fourier transform. And in fact, this is a generalization of the Fourier transform, as we'll see later on. So this Koopman mode decomposition goes back, to example, to this paper of Igor in 2005. Okay, so that's why spectra. There's lots of interest in this, as I'm sure lots of you are aware. So I did the fun exercise yesterday of typing Koopman into Google Scholar, and I restricted myself to since 2004. So there were two breakthrough papers which really helped launch the current interest, and the first of these was in 2004. But you can see that since then there have been about 82,000 papers on Koopman operators. So it's a very hot topic at the moment. But that being said, there are lots of challenges with this framework, and a lot of these challenges are to do with the fact that we live in infinite dimensions, and that's really the message of this talk, is how to overcome some of those challenges. Okay, so there's a paper here, Applied Koopmanism, and then a book of Brunton and Kutz, where they say that global understanding of nonlinear dynamics in state space is a mathematical grand challenge of the 21st century. Okay, so Koopman operators provide such an understanding because you've got a global linearization of your dynamics. But challenges associated with the Koopman framework include continuous spectra. So not all of the spectrum consists of eigenfunctions. Lack of finite dimensional invariant subspaces. So you might discretize K to look at a finite subspace, but then you might have closure issues if that's not invariant. Spectral pollution. So when we discretize the operator K to a finite matrix and compute eigenvalues, those eigenvalues sometimes have nothing to do with the spectral properties of the actual operator itself. So you get pollution in the spectral approximation. So we'll see an example of that in 2 slides' time. Chaotic behavior can also be very difficult. So solutions to these problems in this talk. We're going to compute smooth approximations of something called spectral measures, which I'll define later on, with explicit high-order convergence rates. Okay, and to deal with possible lack of finite dimensional invariant subspaces, I'm going to seek to compute the spectral properties of K, the Koopman operator, directly instead of restricting K to a finite dimensional subspace. This will allow me to also compute certain residuals that are associated with the spectrum with error control that allows me to provide convergence to the spectrum without spectral pollution. And you can prove this, and it's also practical as well. And then all of the algorithms that I'm going to talk about can handle chaotic systems because they all use one-step snapshot trajectory data. And we'll actually see examples of chaotic systems being treated. And often continuous spectra, by the way, is a hallmark of a chaotic system, but not always. Okay, so without further ado, part 1, computing residuals and spectra. So throughout this part, I'm going to be dealing with general Koopman operators. Okay, so there's no restrictive assumptions such as discrete spectra or invariant subspaces or anything like that. Completely general Koopman operators. Okay, so I'm going to start off by looking at something called extended dynamic mode decomposition. So a lot of you are probably familiar with dynamic mode decomposition, which I won't describe, but is sort of you can view the extended version as a generalization of that. And this goes back to a paper of Williams and co-authors in 2015. So what they do is they study the Koopman operator on a subspace of spanned by some functions or dictionaries. Okay, so psi j are just some observables. And for notational convenience, I'm going to collect these dictionary elements in this quasi-matrix here. Okay, so each column just corresponds to the evaluation of a different dictionary. And I'm going to look at these two matrices, psi x, which is just the dictionary evaluated on the x points. Remember, we have snapshot data x and y, so that y is equal to f of x. And then similarly, psi y is just going to be the dictionary evaluated at the y points. So what EDMD seeks to do is construct a matrix so that the Koopman operator looks like a matrix acting on the coefficients when you expand functions in this space. So let's say we have G in the span of this dictionary. Then G is this sum here, of these observables or these functions, and we seek a finite matrix K EDMD, so that the Koopman operator acting on G is approximately given by this sum here, where we're just acting on the coefficients with this matrix. So let's say we try and minimize the error of this approximation, or the integrated error, over the state space omega. Then we end up with this minimization problem here. And the idea is very simple. Let's approximate this integral with quadrature. And for the quadrature points, I'm going to take x to be the snapshot data that I have, right? The x1 through to xm. And then you have weights of the quadrature, and you get this approximation here. So, for example, if the x's are chosen uniformly at random according to some law, then you could take the weights to be 1 over m, so uniform weights. But there are other scenarios that you could treat as well. Okay, so this reduces the problem to a weighted least squares problem. Okay, and you can write down an explicit solution in terms of these matrices, psi x and psi y, and also this diagonal weight matrix. The dagger here is just the pseudo inverse. But the key thing to note from this slide is this convergence. So in a lot of different scenarios, you can prove that as the number of data points goes to infinity, these two matrices will converge to the Gram matrix of the dictionary, and also a Galerkin approximation of K, respectively. So that's the key thing to take away from this slide. Oh, the inner product here corresponds to the Hilbert space L2 omega. Okay, so that's just what these angled brackets mean. Okay, so that's EDMD. So let's see what happens when we compute the eigenvalues of that matrix approximation. So I've taken here the nonlinear pendulum, okay, and I've turned it into a discrete dynamical system by evaluating every half second in this particular case. So x1 is just the angle here with the pendulum, and the state space, it's periodic domain for this angle, and then you've got r for the momentum, so the x2. Okay, so I'm going to show a video on the right-hand side. So remember, nk is the size of the dictionary, or the size of the matrix approximation here. And the magenta dots will be the eigenvalues, the EDMD eigenvalues. Now, for this particular example, the spectrum is the unit circle. Okay, so anything that's far from the unit circle corresponds to this spectral pollution that I'm talking about. There'll also be a gray set, which will increase and wrap around the spectrum, which will correspond to something called pseudospectra, which I'll define in a few slides' time. But you can think of this as fattened up versions of the spectrum. And using our framework, you can compute this pseudospectrum with error bounds, and this allows you to tell which of the eigenvalues are accurate and which are not. Okay, so we increase the truncation size. We see that we're approximating the pseudospectrum, and we get lots of spectral pollution inside the circle here, but these eigenvalues are pretty reliable. But this allows us to tell which of the EDMD eigenvalues are accurate and which are not. Okay, so just let the video finish. Great, so you can see that you get the spectral pollution, and you can get this set telling you how to avoid it. Okay, so how do we do this? Well, I'm going to introduce something called residual DMD, or ResDMD. And the idea is really simple. So suppose I have an observable G that lives inside the span of my dictionary. Okay, so the expansion here, and lambda. And suppose that this is a candidate eigenfunction eigenvalue pair. Then a good way of approximating how close they are to an actual eigenfunction eigenvalue pair is to look at this squared residual. And you can expand this out in terms of these 4 inner products. Now, remember the 2 inner products we had 2 slides previously. We had this inner product and this inner product. This inner product is just the, you can think of it as the adjoint or conjugate of this inner product here. But we've got this new type of inner product here where K appears on both sides. So the idea is really simple. You can approximate this double inner product using psi y. Okay, so psi y w psi y. So remember, we previously had this matrix here and this matrix. So now we have this additional matrix. And again, you can show that in the large data limit, this will converge to this inner product here. Okay, so we have a way of computing residuals, hence the name. So we want to do a relative residual. Okay, so that's just what this formula here is. And the algorithm for avoiding spectral pollution is very simple. So first of all, you compute the EDMD matrix, its eigenvalues, its eigenvectors. Okay, and then for each eigenpair, you compute this residual, and then you discard the eigenpair if the residual is greater than a specified tolerance epsilon. So you can prove the following. Okay, if lambda m is the eigenvalue output of this, then in the limit of large data, the reciprocal of this, this is the resolvent norm, or this shifted inverse is at most epsilon. So a little bit about this. This tells you how close you are to the spectrum. Okay, so as you get close to the spectrum, this inverse becomes more and more ill-conditioned, and this resolvent will blow up, so its reciprocal will go to 0. Okay, so you can think of this as some type of error bound on how close you are to the spectrum. Okay, now a word of warning about this algorithm. All we're doing is cleaning up the eigenvalues of EDMD, right? We have no guarantee that we're going to approximate all of the spectrum. And in fact, it's very easy to develop counterexamples that show that you don't in general. So whilst we avoid spectral pollution, we're not guaranteed to approximate all of the spectrum. So to overcome that, we also compute something called pseudospectra. So given epsilon greater than 0, the pseudospectra is just this union of perturbed spectra, okay, where I perturbed the operator k by some b of size at most epsilon. Okay, so this is sort of a notion of how stable the spectrum is. And you can prove that as epsilon goes to 0, this will converge to the spectrum in an appropriate sense. So this is how we compute pseudospectra. So you compute the 3 matrices. Remember, we had the first 2 matrices from EDMD and this new matrix for ResDMD. And for each Z in a computational grid, we compute the minimum residual over our span of dictionary, which is actually just a generalized SVD problem. Okay, so it's not hard to do this. And then you compute the corresponding singular vectors. And then the output is simply the grid points which have a minimum residual less than epsilon and approximate eigenfunctions. So whilst this algorithm looks very simple, you can prove under certain conditions on your grid that the output is guaranteed to be inside the pseudospectrum. So you get a notion of error control and no spectral pollution. And as your dictionary size increases, you converge uniformly to the pseudospectrum, okay, on bounded or compact subsets of C. Okay, so that's the algorithm that I showed you for the pendulum. So let's go back to the pendulum and let's look at these approximate eigenfunctions. Okay, so you can think of these as rigorously computed eigenfunctions. They're not quite the same thing, but it's a good way to think about it. So here I've got different lambda on the unit circle, okay? And I've got the corresponding approximate eigenfunctions. The color represents the complex arguments, the shadowed steps, or the modulus. And all of the residuals for these modes are smaller than 0.05, which you can make smaller by increasing the size of the dictionary. Okay, so you can compute these approximate eigenfunctions, and you also have a robustness guarantee. So that's the pendulum. Let's look at something a bit more difficult, the Lorentz system. So I'm going to look at the Lorentz system on the whole of R3 rather than just on its attractor. Okay, so it's governed by this coupled system of 3 ODEs. So rho here is, I think, the Rayleigh number, which you can think of as how chaotic the system is. So the top row will correspond to Lorentz's original system. The bottom row will correspond to an 11-dimensional extension from this paper down here. Okay, and the contours show the pseudospectral contours. Okay, so that's the size of the epsilon. And the magenta show the eigenvalues of EDMD. So you can tell using the contours, for example, that this eigenvalue corresponds to pollution, whereas these ones don't. Okay, so you can compute these pictures. You can get a sense of the spectrum and the pseudo-spectrum. For example, here are the eigenvalues and the residuals, okay, Rj, for Lorentz, extended Lorentz, for 3 different values. I've only plotted a finite number of the eigenvalues below 6. There are more, but this just gives you an idea of what you can do with algorithm. Okay, oh, and by the way, this is particularly for large rho here. So when rho is, I think, greater than 25, this is a chaotic system, right? So we're able to do this even for chaotic systems as well. Okay, part 2, dealing with continuous spectra. And to do that, I'm going to compute something called spectral measures, which I'll introduce in a second. And in this part, the only assumption I make is that the dynamics are measure preserving. For example, I don't assume that they are ergodic. And this is equivalent to K being an isometry, which just means it preserves the size of your observables G. And the spectrum in this case is guaranteed to be inside the unit disk. Okay, so to introduce spectral measures, it's helpful to first revisit the more familiar finite dimensional case. So suppose I have a matrix A, an n by n matrix, which commutes with its adjoints, this A star. So that just means the matrix is normal. Then there's an orthonormal basis of eigenvectors Vj, so that you have these 2 decompositions. So each of these Vj star here are a projection onto the corresponding eigenspace. And here I'm just rewriting P as a sum of these projections acting on itself. Okay, so this is just telling you that you're decomposing the space. And then, of course, diagonalization says that AV is equal to this formula here, where A just acts trivially on each of these eigenspaces, right, with the multiplication by the eigenvalue. So when we jump to infinite dimensions, say an operator L on a Hilbert space, typically there's no longer even a basis of eigenvectors. Okay, so you can't write down something like this. But the spectral theorem says that you can do something very similar, which is to replace these projections here by something called a projection valued spectral measure. So this sounds horribly scary, but on the next slide, I'm going to try and convince you that it's just a bit like a Fourier transform. And what this does is, given an appropriate set, okay, you take the measure of that set, and rather than being a scalar, it gives you back a projection, telling you how much of the operator L is concentrated on that set. Okay, so you can write any G, any function G in your Hilbert space as now an integral over these projections, over the spectrum. Okay, so you replace the sum with an integral, and similarly, L acting on G is given by the same formula up here, but now with an integral over projections. And we're actually interested in scalar valued spectral measures, which are given by taking these projection valued measures and projecting on an observable G and then taking the inner product. Okay, so I promised that this wasn't too scary. So let me try and convince you why that holds. So for example, let's take the second order derivative operator. Okay, and let's first look at the periodic interval minus pi pi. Then the spectrum of this operator is just n squared for non-negative integers. Okay, so you get discrete spectrum, these points here along the real line. Now the projection valued measure in this case can be written down in terms of Fourier series. So given a G, we have Fourier coefficients, then the projection valued measure on an interval AB just gives you back the Fourier series where you restrict the frequencies between A and B. Similarly, when you look at the scalar valued versions, you get the energy or the size of G with frequencies on this interval. Okay, so now let's look at what happens when we go from the finite interval to the whole real line. The spectrum now becomes the half line and it's continuous, and we replace the Fourier series by the Fourier transform. And you get exactly the same formulae as before, but we've replaced this sum by this integral. So the way to think about spectral measures It's just as a generalized Fourier transform that's sort of tailor-made to your operator L. All right, so it diagonalizes the operator. And by doing that, you can recover its spectral properties and do lots of interesting things. So let's now look at this in the context of Koopman operators. And so here the spectral measures are on the periodic interval minus pi pi. Okay, you can use something called Lebesgue's decomposition theorem to split up that spectral measure into a discrete part and a continuous part. Now the discrete part consists of a sum of Diracs centered at the eigenvalues of the Koopman operator, an absolutely continuous component with spectral density rho g, and a singular continuous component, which I'm not going to really talk about, but the algorithms that we develop can also deal with this part. Okay, so given a g, you can write it out as we saw near the start in terms of a sum of eigenfunctions and this continuous component, which corresponds to this part of the spectral measure. And you can look at g of x of n using the composition with the Koopman operator, and you get the usual thing, okay, where you get powers of the eigenvalues here for the discrete part and this Fourier transform type part here. So in other words, computing these spectral measures diagonalizes the Koopman operator and also provides you with Koopman mode decomposition. Okay, so it's really useful to be able to compute these. All right, so that's spectral measures. Now I'm going to show you a way of computing those spectral measures using a Plamelge type formula. So the starting point is the Poisson kernel for the unit disk, given by this, this formula here. So the key thing about the Poisson kernel is you have this parameter epsilon, which acts as a smoothing parameter. So as epsilon goes to 0, this will get closer and closer to a Dirac. So it's an approximation of the identity, is what analysts would call it. I'm also going to need this generalized Cauchy transform of the spectral measure. Okay, so the idea is to take our spectral measure and take a convolution with this smoothing kernel. Okay, so you can think of this as a smoothed version of the spectral measure, and it's actually a function, right? Even though this is a measure. And why have I written out these generalized Cauchy transforms? Well, you can rewrite this convolution here in terms of this Plamelge type formula, right? These difference of Cauchy transforms. And in turn, you can actually go away and derive a formula for this, this sum here in terms of these inner products with the shifted inverses of K. Now, importantly, I only have to evaluate this inverse for a shift outside the unit disk. So remember, the Koopman operator K has spectrum, so eigenvalues and continuous spectra, inside the disk. So this inverse won't exist inside the disk, but that doesn't matter for this purpose because I can get away with only evaluating outside the disk. So the idea is to approximate these inverses, which just consists of solving linear systems, by using the ResDMD matrices for a truncation size nk. So if you forget everything from this slide, that's the main idea. Okay, so we have these smoothed measures that we're approximating with a given truncation size nk. Right, so let's look at a quick example of that. So I'm going to look at this infinite unitary matrix. And the reason I've chosen this is that it has a known spectral measure, but it's actually a generalization of Bernoulli shifts, and is a typical building block of many dynamical systems with something called Lebesgue spectrum. So that's just the operator that I'm going to do for the next couple of slides. So our first idea is to fix the ResDMD truncation size nk and vary the smoothing parameter epsilon. So on the right here in black shows the spectral measure. Remember, it's between minus pi and pi of the infinite matrix, okay, of the Koopman operator. The red shows the smoothed approximation, all right, using ResDMD and that convolution formula. These red dots here, or these red circles, correspond to where I evaluate those shifted inverses, right? And as they approach the spectrum of the Koopman operator, okay, as epsilon goes to 0, we'd expect something potentially bad to happen. So let's see what happens. We're okay for a bit, and then it suddenly becomes very unstable. And the reason it's becoming unstable is because we're actually picking up the discrete spectrum of the truncated Koopman operator rather than the Koopman operator itself. Okay, so as we get closer and closer to the spectrum, we're approximating the spectral measure of the finite truncated matrix or discretized Koopman operator, which necessarily only has discrete spectrum. So that's what these spikes are. Okay, you might say, well, that's because I took epsilon too small. What happens if I fix epsilon, say 0.1? So these poles are fixed here, and then I increase the truncation size. And it's very nice and stable, and in fact converges, but it converges to something that's too smooth. So this is an over-smoothed approximation of the spectral measure, okay, which will actually correspond to the convolution of this black curve with the Poisson kernel with smoothing parameter 0.1. Okay, so the solution to this problem, so we can't fix n, we can't fix epsilon, but we can choose them both adaptively. For example, given an epsilon, we can choose the truncation size adaptively. Given a truncation size, we can in turn choose epsilon adaptively. And I'm not going to go through the details of how you do this, but it turns out that you can do this in a completely rigorous and robust manner using this new ResDMD matrix to compute residuals. So let's have a look at what happens. Okay, so it's now completely stable, even as we approach the spectrum. So you might think that this is the end of the story of computing spectral measures, but definitely not. It turns out that this is very slow in terms of the convergence rate. So as the smoothing parameter epsilon goes to 0, the approximation error is order epsilon log 1 over epsilon. So this is just the pointwise error for the spectral density, okay, that curve that we saw before. And you see this very slow convergence. But as epsilon goes to 0, the truncation size that you need, okay, so the size of your discretized Koopman operator blows up. So you can see this in these pictures here. So these show the errors due to discretization for different epsilon. And the key point is that for smaller epsilon, you need a much larger n to get a given accuracy. And this is critical in data-driven computations where you want the size of your discretization to be as small as possible, right? Because it can be very expensive to form that discretization. So the question is, can we improve this convergence rate in epsilon? And the answer is yes. And the simple idea is to replace the Poisson kernel by this more general-looking rational kernel. Okay, and there's a simple way to select these Zj and these coefficients here that I won't go into. But the key point is that you have a very similar convolution formula as before, okay, in terms of these generalized Cauchy transforms. And if this kernel satisfies certain properties, you can get much faster rates of convergence. Okay, so we compute these generalized Cauchy transforms using ResDMD as before. And let's have a look at this in action for m equals 6. So m here is the order of convergence, or the order of this kernel. And you'll see that I have 6 poles here, or six of those shifted inverses, or generalized Cauchy transforms, which will converge to the same point on the unit circle. Okay, so you get much faster rates of convergence. Okay, so epsilon is 0.1, and we're already converging to the spectral measure, and we're not having to get too close to the spectrum where things become behaved. Okay, so that's higher order kernels. Oops, there we go. This is the end result. So this is the Poisson kernel on the left. Okay, so this Plamelge type formula, over smoothed. Now m equals 6, a generalized Plamelge type formula, and we get a much better approximation. These are the convergence rates. Okay, so we can prove rigorous order m convergence for the pointwise recovery of rho g. Remember, rho g is, let me just go back a few slides, the density of the absolute continuous part of the spectral measure. Okay, so we have fast convergence for that, pointwise sense, and also LP, or average sense. Also weak convergence. So if you integrate this approximation against test function, a periodic continuous test function, then you'll gain convergence to the appropriate integral with fast convergence rates. You can also use this to recover discrete parts of the measure, which correspond to the eigenvalues of K. So, for example, this shows the corresponding plot for this curve here, but now with higher order rates of convergence. So this is approximating the spectral density. This is much faster. And we also have a practical algorithm that uses the QZ algorithm to do this fast in order nk squared operations, where nk is the truncation size of, the discretization size of these ResDMD matrices. Okay, so now I'm just going to end this part with two simple examples. The first is the tent map in dimension 1. Okay, so here f is just this nonlinear hat function. Omega is just the interval 0, 1. And I'm going to choose as my observable this arbitrary non-continuous function g. This shows the smooth approximations. So let me just explain a bit about this example. So there's an eigenvalue at 0, which in fact corresponds to just the observable 1. Okay, so that happens a lot when you study Koopman operators. And you also have an absolutely continuous spectral component as well with this density function. So the blue shows the Poisson kernel and an oversmoothed approximation. Okay, so the eigenvalue is not localized, and in turn the spectral measure away from the singularity is not well approximated. Now, if you go to m equals 6, you get a much better approximation of both the continuous components and also the discrete component here. So you avoid oversmoothing and you have better localization of singular parts. Let's look at the double pendulum next. So this is a chaotic Hamiltonian system. Okay, so the picture is this. So you have two pendula attached to each other with these two angles here. They're governed by this very complicated looking coupled system of 4 ODEs, where P1 and P2 are these generalized momenta here. And I'm going to look at, let me just double check. Oh yeah, time step 1 second for this example. And I'm going to compute spectral measures as before, but now with respect to four different observable functions. Okay, so you have the first Fourier mode of the first angle, similarly the first Fourier mode of the second angle. Okay, and you see these peaks around 0. And m equals 1, the Poisson kernel is oversmoothed. M equals 6 is much more accurate. And in fact, I verify this against smaller smoothing parameters and other kernels as well. This is the same plots, but now for the momenta P1 and P2. And you can see you get a much more interesting spectral measure, suggesting perhaps more complicated interaction with the dynamics. Okay, so that's spectral measures. So now let's make it a bit harder. Let's raise the stakes. So previously, I had I'd done small dimensions D, right? So I think the highest one I did was the extended Lorentz system in 11 dimensions. So we're now going to look at high dimensional dynamical systems, which is what you typically have in applications, and also learned dictionaries. So let's begin with an example. And we'll see this example at the end. Suppose I have some flow. Okay, so in this case, past a cascade of aerofoils. So this is the leading edge. This is the trailing edge. And let's suppose that I look at a scalar field at each of these grid or mesh points, right? See, you can see the zoomed in section. So D, the ambient dimension, will just be the number of grid or mesh points. So this is a very common thing in fluid applications of DMD, for example. Now, let's suppose that I, for my dictionary, look at polynomials up to total degree 5, okay, to try and capture the nonlinear dynamics. If I have a small 5 by 5 grid, okay, so this is absolutely tiny, the size of my discretized matrices will be 50,000, which is just about doable on a desktop computer. But the example that we're going to look at later, D is 300,000. And in that case, the discretized size is 2 times 10 to the 25, which is much, much bigger than the number of stars in the known universe, right? So there's no chance we can ever hope to deal with this size of discretization. So the conclusion from this example is that using handcrafted dictionaries is not really feasible when D is larger than about 25. So we need to do something else. Okay, so I'm going to use an idea from kernelized EDMD. So this is due to this paper here of Williams and co-authors in 2015. And they used the kernel trick to speed up the computations of EDMD so that they only scale linearly with the dimension D. So what they do is they form a reduced matrix of size m by m, which shares a subset of the eigenvalues of the usual EDMD matrix, right, which has size nk by nk. And you can view this as implicitly learning a dictionary. So if you look at the eigenfunctions of this, or eigenvectors which form eigenfunctions of this finite matrix. Okay, so that's all very well and good, but this kernelized EDMD still suffers from the same issues that we saw before, for example, spectral pollution, and in fact, probably even more so because there's not necessarily robustness guarantees when you apply the kernel trick. Okay, so you have challenges of continuous spectra, lack of finite dimensional invariant subspaces, spectral pollution, and also chaotic behavior. So the good news is that you can use ResDMD and combine it with kernelized EDMD to overcome these challenges. And the idea is to have 2 sets of snapshot data. So you can view this as a test set and a validation set. So I have my first set, x, y, okay, snapshot data as before, and now I have a second set, x hat and y hat. And there's this 3-step procedure. So in the first step, I apply kernel EDMD to this first snapshot data. I then compute the dominant nk -- eigenvectors of this reduced matrix, which gives me a learned dictionary, psi j. Okay, and then I simply apply the above ResDMD algorithms with this second snapshot data and the learned dictionary. And the key advantage is you can still apply the above convergence theory, right? And you can also check afterwards how accurate or how well your dictionary is performing by doing things like computing the residuals and pseudospectra and stuff like that. So this overcomes the challenges on the previous slide, and I'm just going to end the talk with 2 fun applications. So the first is in molecular dynamics. Okay, so this is where you simulate atoms and molecules using Newton's laws of motion. Okay, so molecules and proteins and things like that have recently been in the news with DeepMind's AlphaFold. So it's a very hot topic. I'm going to use a data set, which is publicly available here, produced on the supercomputer Anton. Okay. I'm going to look at a certain protein known as ADK. So don't ask me what that stands for, because I won't be able to pronounce it. But it's important for phosphate reactions in the cell, for example. And this protein has 3 key parts. So there's this core domain, this LID domain, and this NMP domain. And then within these 2 parts, so the core domain is pretty stable, but the LID and the NMP sort of fold and rotate around it. There are 2 key parts of both of these domains, which I've labeled in magenta here. And on those parts, you have 2 dihedral angles, psi and phi, which control a lot of the dynamics of this protein. So I'm going to compute the spectral measures with respect to those 2 observables. Okay, so those are the G. So here's the result for the LID domain. You get this nice, beautiful spectral measure. Here's the result for the NMP domain. Okay, so these were computed using that 6th order method that I talked about. And this is an ambient dimension 20,000, right? So the dimension corresponds to all of the atoms in this molecule and all of their momenta. So the system is Hamiltonian. Okay, and we're able to compute these spectral measures robustly using kernelized ResDMD. So that's spectral measures. Let's end with Koopman modes. So I'm going to look at turbulent flow past a cascade of aerofoils in ambient dimension 300,000. So that corresponds to the number of points that I sample my scalars, in this case pressure. So the physical setup is this. So I have an inlet, I have a periodic cascade of these aerofoils or turbines, and then I have an outlet. And I'm interested in how the flow interacts with these turbines and produces noise. So this is very important for noise reduction for aeroplanes, for example. And the data set I'm going to use is from this paper down here, where they do a large eddy simulation. And actually they used, if I go back, this mesh here. So it's a very high fidelity computation. And these are the results. So let me explain what's going on here. So I've looked at the Koopman modes for different frequencies. Okay, these are the lambda, the columns. I've done the Koopman mode decomposition for DMD. So you can think of that as a version of EDMD, but with linear dictionary, a linear dictionary. And these are the corresponding Koopman modes. ResDMD, remember, chooses nonlinear functions as the dictionary. So in this case, you learn them because we use the kernelized version. And I also have the computed residuals of these modes. So this gives you a notion of robustness or error control. Okay. And each of these frequencies are physically important for noise reduction. And this is fully turbulent flow. So the I think the Reynolds number is about 10 to the 5 or something. So it's pretty big. Okay, so let's look at the differences between these two rows. So here you see stronger acoustic vibrations, which is a nonlinear effect. And this is very important for controlling whether these turbines are damaged by the flow. In this column here, you see nonlinear turbulent fluctuations in the wake or beyond the trailing edge of the aerofoils, which aren't really present in the DMD or the linear case. For DMD, you have this acoustic source, this nice acoustic source here, which is completely deformed when you go to nonlinear dynamics. So sort of the moral from this picture is that ResDMD is potentially very useful for two reasons. First of all, you can capture the fully nonlinear effects. And second of all, and I think this is really important for applications, you get this robustness guarantee as well. And we can do this even in ambient dimension 300,000. Okay, so to end, I provided some rigorous and practical algorithms that overcame the challenges of continuous spectra, lack of finite dimensional invariant subspaces, spectral pollution, and also chaotic behavior. Okay, so all of the algorithms were based on single time step trajectory data. Okay, so we dealt with chaotic systems. Part one computed spectra, pseudospectra, and residuals of general Koopman operators. And the key take-home idea was this new matrix that allowed us to compute the residual. And this new matrix was available from the data we already had. And this led to ResDMD. Part two computed spectral measures of measure-preserving systems with high-order convergence. And we were able to recover the density of the continuous spectrum, the discrete spectrum, and also weak convergence. And the idea here was convolution with rational kernels through the resolvent and ResDMD. And then finally, we dealt with high-dimensional dynamical systems by using the kernel trick to learn a dictionary and then applying these ResDMD algorithms in part one and part two. So details and code can be found on my website here. So I will post these slides on my website at the end if you want any of the pictures and references as well. And if you have any additional comments or questions, then please get in touch. That's all I have to say. Thanks for listening.
All right. Thanks very much, Matt, for a really interesting, exciting talk. Let's see if there are any questions. Let me start with one, not yet. Let me start with one. So there are two approaches to continuous spectrum computation that are out there and that are rigorous. And one of them, I mean, prior to this work, One of them is Dimitri Giannakis's group at NYU, and what they mostly do is kernelize, also using kernelized methods with and doing the associated compactification, and they prove that in the limit everything converges finally, and it's also pseudo-spectral. And then the other one is the Christophe Darboux kind of kernel as well. So it seems that everything is kernel, right? Everything is kernelized in this world, as I think it should be. But can you give us some light on kind of contrasts, advantages of one versus the other?
Yeah, exactly. Yeah, that's a great question. And those were the two works that I had seen as well on spectral measures. Okay, so first off, I think both of those examples are restricted to ergodic systems. And the way they do that is they compute these. Okay, so these matrices here, for example, oops, or similar in the products. It's not exactly these matrices by using Birkhoff's ergodic theorem, right? So here, because of this framework, you can deal with more general systems, or actually more general types of data. So you might not have one long trajectory. You might have lots of short trajectory data, which fits into this framework. You can also do it for long trajectory by stacking. So that's one of the first key differences. So you can deal with different types of trajectory data, and you're not just looking at ergodic systems. I know that has pros and cons. For example, if you want to study the Lorentz attractor or something like that, you're going to have to use some sort of ergodic method to eventually live on the Lorentz attractor. But you can still use these ResDMD methods with that way of collecting data as well. So you can view this as sort of a framework of taking all those different ways of trajectory and these quadrature rules, and you can view them as one sort of unified way. Now, once you've got that, there's actual quite a lot of difference between what you're actually doing with that trajectory data. So yeah, probably the most similar example is the Christophe Darboux kernel, right? And there, I think the difference is that rather than taking those, I think it's those modes, Fourier modes of the measure, and then recovering a spectral measure, what you're actually doing here is doing a pointwise smoothing. So there's no sort of there's no Fourier series involved. And that means that you can get explicit convergence rates. So I might be wrong here, but I don't think there are convergence rates for the Christophe Darboux way of computing things. But there are lots of similarities. For example, when I talk about, we can, where is it? We can recover, discrete spectra. It's exactly the same type of method where you take this smooth approximation of the kernel, you multiply by some constant times epsilon, the smoothing parameter, and this will give you spikes at the discrete spectra. So you can actually view epsilon here as the reciprocal of n, the number of Fourier modes you have of your expansion in that particular method. So yeah, so that's one of the main differences. In terms of pseudospectra, I think that there are no sort of restrictions in terms of needing to be in a gap of the essential spectrum, or needing to be near the discrete spectrum in order to get these types of error bounds. So I think that the results hold in a slightly more general case, but the price you pay for that is that you don't always get convergence rates. So you don't know how fast this approximates the pseudospectrum, for example, which I think you do in some cases when you look at isolated points in the discrete spectrum. The method is very different, of course, because you don't actually do a compactification or anything like that. You're just sort of by hand. Well, you're computing these matrices and then computing the residuals.
I mean First of all, that it's different types of convergence rates, right? So you have them in time because you're taking samples. As you pointed out, the main difference is in that case, you're taking samples along a trajectory. And you can get convergence rates in that context.
Would that be corresponding to the number of data points going to?
Yes.
Yeah. So by convergence rate, I'm meaning the smoothing parameter, which would be correspond in your case to the number of Fourier series n that you use.
Correct. Yeah.
So you would get convergence rates for these things. For example, square root of 1 over m if you're doing random or the ergodic systems as well.
Yeah, there are convergence results for that as well. I don't now recall whether we explicitly wrote them down, but using Szego type theorems, you can actually get convergence rates, and as you would guess, I think, given
I've definitely read it somewhere in one of your papers.
So you can get convergence rates as m goes to infinity in that case as well. Any questions from the rest of the group at this point?
I have one.
All right, Matthias, go.
So this new matrix, V star W, V Y.
Yeah.
When you say that limit, are you assuming that the measure with the inner product is preserved by the dynamics, or is it an arbitrary measure?
Oh, no. It's arbitrary. So the important thing for this convergence here is that this quadrature rule converges. So this is very similar to what we were just discussing with the previous question, where you're looking at convergence of approximating Fourier series of measures. So, for example, if you take x and pick it at random according to this, if it's a probability measure, then your weights would be uniform weights, and you get standard Monte Carlo rates of convergence under some annoying technical conditions. Similarly, if it's ergodic, you get ergodic convergence rates, or you can do higher order quadrature and things like that. So there's a lot of theory telling you precisely when you get convergence of these matrices to these inner products, and also this inner product here. So yeah, I'm not assuming measure preserving or anything like that. I'm just assuming that the quadrature rule that I'm employing converges.
Okay.
But you are in L2, so somehow is going to connect to my other questions. So somehow, morally, you can only sort of do L2 if you're in the measure preserving case.
Oh, so an example where it's the Lorentz system, not on the attractor. So here, what I'm actually doing is, rather than doing random points or ergodic sampling, I'm using I'm letting my algorithm choose those initial points, and they'll correspond to a tensor grid, which is just integration in these high-dimensional dynamical systems. So in this case, it's not measure preserving, and the spectrum is outside the unit circle. So yes, I think actually that's an excellent point in terms of answering the first question as well. A big key difference is that for the pseudo-spectral stuff, you don't need your system to be measure preserving. So you can study things like the pre-transient behavior of the dynamical system, which is exactly what this Lorentz example is doing.
So let me see if anybody else in the audience has. I'll connect to that, but let me see if not to usurp the podium. Does anybody else have a question?
I would have a question, if I may.
Go. And hi, Peter. We were met, I think, alive, but welcome to the seminar.
Yeah, thank you very much. Yeah, we maybe exchanged an email or something, but yeah, we haven't met in person, sadly. But hopefully next year, I guess.
Hopefully.
Yeah.
With Omicron, we don't know.
Yeah. I was wondering, you've mentioned learning a dictionary and EDMD, right? It's somewhere close to this slide, or I think before, right? Probably before.
Yes.
Way before, yeah.
Yeah, it's this stuff.
Yeah, so you basically mentioned the kernel trick and the kernelized EDMD method, right?
Yeah.
I was wondering, you say you learn a dictionary. In what sense did you mean you learn a dictionary? For example, I don't know, you could use some basis functions like RBFs. That's often used. So my question would be, how do you optimize the hyperparameters of the kernel function in your scenario?
Very, 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 very good question. So, by learned, I just mean that this matrix here obviously depends on the snapshot data. So in that sense, you're learning dictionary by looking at the eigenfunctions. But there's a lot of tuning when you use these kernels. So we use the Gaussian kernel with just the length scale, and that Gaussian was just chosen to normalize everything to mean zero when it has mean zero, for example. I didn't really focus that much on this because one of the nice things is because you can compute residuals and things like that, you can tell when your kernel or your tuning is behaving badly. So you can, for example, let's say we have a measure preserving system. So we know the spectrum is the unit circle. We can then compute pseudo spectra. And remember that video where we saw the pseudo spectra increasing around the circle? Typically what happens when you have a bad kernel or a bad learned dictionary is you don't get a very good approximation of the circle. You only get little bits. So you can play around with things like that to be able to tell whether your kernel or your learned dictionary is behaving as it should. So that's kind of it. It's still it still has all of the problems of how do I choose my learning? How do I choose my hyperparameters and things like that? But the nice thing here is that you can tell afterwards whether it's worked. So not just for spectral measures, but also for these residuals. How small are these residuals? Is it accurate and things like that? So one of the things that you could do, you don't have to use this kernel trick. You could use other methods of learning dictionaries and things like that, and you'd still be able to use the same sort of verification afterwards of whether your tuning has worked.
Yeah, I see your point. I think it's very interesting that basically you kind of move away from this issue that EDMD has of these spurious spectra, and basically afterwards you can basically check if your guess of the dictionary was good or not.
Exactly.
But my point, just maybe to think about, is that in a sense, this kernel trick that's done with EDMD kernelized methods is not actually a learned dictionary. Because usually kernel methods don't specify any of the arguments. They are both from the data you've seen. And basically you probably need to make a grid or specify basically the centers of the RBFs, right? Which then kind of makes also a pre-specified dictionary.
But it's still learned in the sense that you're learning. Okay, so you're not using all of the eigenfunctions of this matrix. You're only using the dominant ones. So you're learning the coefficients for the expansions in those RBFs. So that in some sense that I think is the bit that's learned. But you're absolutely right. The centers.
But basically, just a thing to think about. I think it would be more, or it could maybe improve convergence or efficiency if one would basically make it really implicit, where you don't need to specify centers, where the centers will be of your data.
Okay.
So basically, where you could actually maybe even concurrently learn the hyperparameters without specifying them. Just something to think about. I think might be.
I guess you could use these residuals and things like that in the loss function, for example. That's a very good idea.
But you know what I mean, basically with not specifying the centers. As soon as you specify them, you're already gone with the kernel trick. You're already specified the features. A neat thing would be maybe through hyperparameters to actually learn the features without specifying the centers. That they're basically all from your data, because centers are not actually from your data in a sense. Making them a fixed dictionary. But really cool stuff to kind of analyze this spuriosity of EDMD methods. Thanks.
Let me see, any other, I have a few more, but any other questions from the rest of the audience? No, not maybe, going back to that question of the functional space, which is very interesting. There is some tricky stuff that comes in when you're considering dissipative systems. And you might have seen, I think I sent you the 2019 paper. We analyzed this a little bit. And I'm wondering, and that pertains to literally what you said, which is sampling, right? So how do you sample? If you have an L2 space, then clearly just letting the trajectory go or doing one step with a single trajectory, everything's fine. But in the case of dissipative dynamics, then it's actually these modified Fock spaces that provide the right framework. And interestingly, they're based on eigenfunctions. So, you know,
So is that corresponding to, are you talking about the choice of function space here?
yes, the choice of function space in a numerical approximation is really the choice of sampling, isn't it?
Mm-hmm.
So when one has a dissipative system, if one chooses L2 with respect to an invariant measure, which is an eigenfunction of a transfer operator, right?
Mm-hmm.
So you gotta say, well, L2 with respect to what? Then you can sample with respect to, let's say, trajectories. And the only thing that you get is eigenvalues and eigenfunctions corresponding to, as you said, the ergodic part of the system, right? So the cyclic part, the part that repeats on the attractor.
Yeah.
But if you want to truly capture the dissipative effects without any doubt, then one has to go to a different functional space, which is really a tensor product between this L2 and an off attractor space that is what I call modified Fock space.
Yeah.
Fock spaces are, you know, you just e to the minus z squared.
Mm-hmm.
Z is your variable on one dimension. It's kind of like a smooth, again, a kernel, right? It's a smoothing. And it's basically an invariant measure of an associated diffusion. So this is a long comment, but the interesting thing I think would be, given how nice these methods are in cleaning up the aspects of EDMD, you know, whether one would be able to do the same, because that's spectral in dissipative systems in this sense. I know you're getting the eigenvalues for dissipative systems. Actually, it's quite interesting. I want to go back to the turbulence part because I know there's something super interesting. But I think you're getting the stuff that pertains to the attractor. So for example, the isochron eigenvalues, they are, of course, something that you can get off the attractor, but they are really pullback from the attractor. They're not really the dissipative part of the dynamics. If you work in these you know, tensor product spaces, then you can get properly dissipative stuff without any doubt. Anyhow, we can continue this discussion. But
no, definitely. Because one of the things that's been sort of perplexing me is that there's always this implicit choice of this measure here, right? This omega. So, for example, for the res, where's the picture here? So, you know, I'm doing R3 and I'm doing a Gaussian measure, which was just chosen because, you know, the K is nice and infinite, and I wanted to look at the dynamics near zero. But there's no sort of, I don't really have any notion at the moment of how you would choose omega, which I think is related to exactly what you're talking about.
And I will, so let me comment on that, but let me also tell everybody that this is getting really into the weeds. So if people are, you know, if they have other things to do, you can probably well leave, because this might continue for a while. Any other questions from the audience before we continue?
I just had a quick question about the if you go to the eigenfunctions of the fluid flow.
Oh, the last example, yeah.
And when you're looking at the residuals.
Yeah.
So each of these eigenfunctions seems to get smaller in magnitude.
Yes, so that's because when you look at the expansion in the eigenfunctions, those coefficients decay. So actually, the size of the Koopman modes, when you expand the pressure in this Koopman mode decomposition, those coefficients decay.
That makes sense. When you compute the residual, are you normalizing to those sizes, or?
Yes, so I'm not. Yeah, exactly. Sorry. Yes, so these are. These residuals are normalized to the size of exactly.
Yeah. Okay, I wasn't sure because it doesn't look like it based on the pictures, but yeah.
Yeah, so really I should have that here. what you see is that the residual increases as you go around the spectrum, which is pretty typical. It's actually harder to, well, you can think of it, right? With a fixed discretization size, it's harder to capture the more oscillatory components. So you had a similar example with the approximate eigenfunctions of the pendulum here. Whereas you go around the circle, it becomes more oscillatory.
Since you brought it here, that's another thing I was going to ask. So what's the norms of these functions?
So they're all normalized. So in this case, they're normalized to have norm 1. But because it's an eigenfunction,
I meant the absolute values. So are they like go at parts and then getting bigger and then getting smaller, or?
So the absolute value are these shaded regions, but that's a good question, because it's really hard to sort of have a picture of how big. So they will sort of go up and down, but they'll eventually decay. So I'm looking at, so x1 is the angle, okay, and I'm looking at the momenta, x2, but I'm looking at all possible momenta over the whole real line, right? So I've actually shown just a snapshot of this eigenfunction. It expands infinitely in those two directions, and it will decay as we shoot off to infinity, which it has to, right? Because it's an approximate eigenfunction, it's not a true eigenfunction, right? Because they might not be normalizable, and it corresponds to these approximations here. So they are actually bona fide functions in this L2 space.
So what I'm asking is, if I remember correctly, the eigenfunctions of the pendulum, it's continuous spectra.
Yeah.
So these eigenfunctions, are they concentrated like mainly on specific rings, basically correspond to the proper energy level?
I expect so. Yeah, I mean, well, you can see it with these sort of.
Yeah, that's what I was kind of wondering about, because you can't really see the norm. So like basically where it switches is that kind of where the magnitude of the eigenfunction is concentrated, and then kind of the other spots. Okay.
Yeah. So really, I think the best way to visualize this would be a 3D plot, right? The size as well, but
I mean, Matthias, you might remember we discussed this theorem, right? There is a theorem in this 2019 paper that says that the continuous spectrum, and I think you would, if you color just the pseudo eigenfunctions that are claimed there,
exactly.
So the proof, you would get exactly this. So this is very nice.
Oh, that's good.
I tend to call them pseudo eigenfunctions because they're pseudo spectrum.
Yeah.
All right. Going back to our discussion on the measures. So interestingly, you chose the Gaussian, which is actually a very good choice. The reason, the reason being that you don't. So I'll come back to that, but you don't know these measures in advance. Even for a pendulum, of course, you do have it, because uniform measure is an invariant measure. But for general dynamical system, you don't have it. Didier and Rion and Milan-Corda and I wrote a paper on how to find invariant measures as well. So I think some of that could be used in combination with these methods. Yeah. So you find it first, and then you sample with respect to that, right? Or the other way is what Hankel DMD does, and I want to ask you the question on that, because that one also doesn't have explosion doesn't have curse of dimensionality. What you basically do is take one observable, and then you take time delays.
Yeah.
So there are two things that are interesting there. You're basically sampling in a function space, and it's a Krylov subspace method. So you're guaranteed that you're going to fill the subspace, and subspace. So that I find really nice. And it would be really interesting how ResDMD would work with that.
Yes, yeah.
But and then the other suggestion is, for dissipative systems, I thought, so there are spectral expansion theorems, just like the one you've shown that I've shown in that 05 paper. Yeah. In the 19th paper, there is a very general spectral expansion theorem that basically tells you the following. If you take an L2 with respect to the invariant measure on the attractor, and you tensor product that in a certain way with an off attractor space, which basically contains you think about shrinking a tractor, quotienting it to a single point,
Mhm.
and then looking at everything else, and you put on that space a measure that actually depends on the eigenfunctions. So just like the measure, just like L2 on the attractor depends on an eigenfunction, which is the invariant, of the Perron-Frobenius. In the same way, this appropriate space of attractor depends on the eigenfunctions themselves. So I think the future is in somehow finding these things iteratively, right? And doing the correct something. That's kind of an interesting thing. And by the way, I thought for a while this might be not crazy important from a practical perspective. After all, you chose Gaussian, which is actually a pretty close choice. You will see that these modified Fock spaces look like Gaussians in eigenfunctions, right? I mean, they have this Gaussian-like property. But then Page and Kurzweil published this paper in which they said that if you do ordinary DMD, which is basically kind of an L2 sense, you get a breakdown for dissipative systems if you have multiple attractors. Another place which I think these methods would be quite useful to analyze this. And by the way, then the functional space you choose becomes actually super important, because if your state cannot be represented analytically by the eigenfunctions, the numerical method breaks down and doesn't give you the correct answer. You might say that it's valid in the whole region of attraction of a point, but actually numerically, when you look at it, it breaks down precisely where you have a breakdown of analyticity. So in the last few years, I started realizing that this is very important. This is starting to be very important from kind of a practical perspective, because when we simulate.
Please send me those papers via email.
I think the functional space one I sent you.
Is that the 2019 one?
There's a 2019 one, and then in section 6, it contains kind of a general discussion of what the spectra for a pretty general class of dissipative systems are in those spaces.
So that was with Spectral plus nilpotent, right? Is that right?
Spectral.
You had this plus nilpotent. You had this.
That's correct. Yeah, that's exactly the part. And it gives this product theorem that replaces the expansion that you shown in the paper today that I did in 05.
Yeah.
So there is an expansion theorem that precisely describes the situation there. And many dissipative systems are very, very, very nice. I mean, they have, if you have something converging to fixed points, you get these lattices, and there are many examples where you can verify the computation precisely. I mean, it's like so the framework for testing numerics is great, right? And
It's much easier than the Lorenz, for example. I actually had a question for you on the Lorenz, which is when I first plotted these plots, I was really perplexed why the eigenvalues seem to be all real. Because the Koopman operator it's clearly not self-adjoint, right? You've got these pseudo-spectral contours. But the EDMD eigenvalues.
You're using Gaussian kernel here, right? I mean,
Gaussian measure.
Yeah. So you're picking up the dissipative part.
Okay.
You're picking up the dissipative part exactly because of that, because you're actually sampling off a tractor. And what you're showing is that these decay modes. Now, there are people that are also going to say, you might be picking up something that's called Polycot resonances. And that's a possibility as well. And I don't remember, I'll dig out the computation of Royal Polycot resonances. So Royal Polycot resonances are very different. Imagine that you have x dot is lambda x, right? Then your eigenfunctions are x, your analytic eigenfunctions are x squared, x cubed.
Yeah.
Right? Just simple monomials. So so in that case, you get eigenvalues lambda squared, lambda cubed, and so on. And these are dissipative. there is another concept that if you have a measure preserving system, of course, if you work in L2, then you get eigenvalues on the unit circle. If you work in a kind of more pliable, smoother space, so with analytic extension, you actually get these eigenvalues that are called Reuel-Polycott resonances. What they represent is how the average of the function locally, basically, but basically how the correlations decay.
Yeah.
How the locally averaged function kind of decays. So it's a very different concept. It's really, it's really dissipation in functional space. It's not dissipation in state space. And one of the outstanding problems, and Matthias and I are looking at this literally right now, is how do you distinguish? Well, you know, which one is the one? So to tell you the truth, I don't know which ones you're getting there. And it's an interesting problem, but you might detect this based on the modes themselves that you're getting, the pseudo eigenfunctions that you're getting. Are they supported on the attractor, or are they supported off attractor?
That's something I didn't look at. That's
one thing that we were confused about is why are we not picking up any complex ones? So not that what these are that we're actually picking up, but why are there no complex ones? What's stopping them? What's stopping our method? Or more generally, should we be expecting purely real?
That is slightly worrisome, but it might be due to the choice of sampling and the one step. Because both us, and I think we might have been the first, and Dimitri's group, Giannakis' group, detected a pseudo eigenfunction in the spectrum of Lorentz that has a very specific frequency to it. That gives, and so if you look at that paper, and then Dimitri's papers and kind of the follow-ups, I don't think this is widely discussed, but I think it's more interesting than people think. There is something very, very coherent about Lorentz. There is almost like a sinusoidal pseudo eigenfunction that is on it. If you look at the plots, you know, it looks like a sinusoid on the Möbius strip or something. And if you sample that, the predictability is great. You will get excellent predictability, you know, for many Lyapunov periods. So it seems you're not picking that up here. You might want to look at it, right? Because there are two independent computations that picked it up. And I remember even in good old times in the 90s, Edgar Knobloch telling me, oh, there is a peak in the Lorentz spectrum, and that peak is an imaginary pair, corresponds to an imaginary pair of eigenvalues of Koopman. But I do have a related question on that, because you seem to have picked up something like that in the turbulence problem that DMD doesn't pick up on it. So that one.
Oh, by the way, for the Lorentz, before we go to that one, I also looked at the continuous time version, and the spectrum was real again. Okay. So
again, Reuel-Polycott resonances might be the culprit, but maybe it's just one step and, you know, Gaussian aspect of it. I'd go after that, but yeah. The bottom one, for example, the middle, shows some clear periodicity in the structures, you know, away from the wake to the right. And that's really fascinating, because you're simulating this at 10 to the 5 Reynolds numbers. You know, you have data at 10 to the 5. So you do seem to, is this corresponding to a real eigenvalue or a?
No, so the eigenvalues
it's right there. Okay, so that's my point. You seem to have found the mode, a pseudo Koopman mode, I call them. That is really interesting, and maybe in more than one of these, because I think I see some periodicity in the other ones as well. You see the not standard, but the initial ideas on homogeneous turbulence that literally come from Cambridge, right? Would presume there is nothing like this, right? there is nothing like this. Kolmogorov would presume there is nothing like this. The reason being that you should have a complete mess of eddies at every scale.
Yeah.
What you're showing is that it isn't. And that, I think, is really interesting. Now, you know, a bona fide fluid dynamicist is going to say, well, clearly you have some turbine blades here and they're going to generate vortices. And obviously, you know, Lippmann and Roshko have shown you that you have coherent structures. So is this picking up in a very rigorous way the coherent structure aspects that Roshko and Lippmann have done? I think that would be really interesting to see. They have done it on, you know, a wake behind a flat plate, I think. If you look at these classic experiments, you know, you might have nice methodology to really say, hey, here is a way of coarse graining. Here is a way of coarse graining the flow in a way that recovers those coherent structures of Lippmann and Roshko. And, you know, that's a little bit of holy grail. There really isn't a method out there that, and you know, you guys being at Cornell and Cambridge, I mean, these are obvious places to make that discovery.
Do you have a reference for that?
I was sent it.
Yeah, great.
I was sent it to you, but it's a very famous, you know, point in the history of fluid mechanics where they pointed out, hey, the homogeneous turbulence idea, not quite. And then people came in right on the heels of this saying, oh, it's all deterministic chaos. And then, of course, we figured out it's not, right? By 90s, that idea was a little bit dead. But so, you know, in some sense, when I was writing papers way back in 4 and 5, and in the all five paper, you can clearly see the references to that. I was thinking about something like this.
Yeah. And,
you know, we found it in Lorentz in low dimensional system, but I think you found it in this turbulent system.
Oh, cool.
I think that's fascinating.
Great.
All right, let's see if we have any other questions.
Do we have time for a quick one?
Go, Michael. I mean, so Michael Banks is also my student, and he has experience in looking at flows like this with DMD that I think we're not very happy, right, Michael?
Well, yeah, it's hard in the ultra high dimensional nonlinear fluids and all that. I would never expect plain old DMD with linear observables to really work. And so it's interesting. You see the acoustic vibrations. I was just going to ask about the pendulum, though, something much more simple. In the pendulum example, I mean, my understanding is that it is a truly completely continuous spectrum system, right? Yeah. I would almost argue that all of the eigenvalues found by EDMD are spectral pollution, even if they exist on the unit circle, right?
So you could still have eigenvalues corresponding to pseudo modes like this. So those in some sense would be more reliable. So you could have, so as you imagine taking your discretization size to infinity, then you can have eigenfunctions which will converge to the spectrum and in that sense be reliable, but you'll still have accumulation points that aren't on the spectrum. So that would be what spectral pollution would be. But yeah, you're right. I mean, so if you look at the end of this figure here, even the ones that are, you know, reasonably accurate, that's still spectral pollution. But you'd expect, although this doesn't always happen, that as your discretization size increases, you'll get ones that accumulate closer and closer to all of the spectrum.
Right. So is there anything special about these 4 eigenvalues that you found?
I see. I know, other than actually, let me play the video again so I can point them out to you. I chose them to have minimum residuals. So I think I can actually even point out, I think it's one close to here, one close to here. Yeah,
because I can see this outline visibly bubbling up around them, right? Yeah. So you, the user, chose these, and they came originally from EDMD. Is that, am I understanding it?
Yeah.
Okay. Okay.
But I could have, for example, chosen a different frequency, and even if an EDMD eigenvalue isn't exactly near that frequency, I can still compute these. Where is it? Here. Yes, I can still compute those pseudo modes even without an EDMD eigenvalue being close. I just pick a point, right? So here I've picked points exactly on the circle, even though the exact EDMD eigenvalues aren't on the circle.
Right. And is there anything stopping you from choosing a dissipative eigenvalue, even though that would be unphysical?
No, I guess not. It would just have a very large residual.
Okay. Okay. Yeah, that was kind of my question, where those eigenvalues came from. Yeah, so thank you.
No, thank you. Great questions.
Yeah, let me see. Just brief other comments. I think the extension to stochastic, Matthias here has done some work on stochastic extensions that you can look up on arXiv. I think that's interesting as well, because once you have noise pollution, you know, the robustness of these methods, and he found that EDMD needs to be updated, especially in its Hankel form. When you take time delays, needs to be upgraded in a certain way. Otherwise, you get another pollution, which is stochastic pollution, I would call it.
Interesting. Yeah.
So Matthias, you might want to send Matt and Alex at least your preprint.
Yes, please do.
Yeah,
this is great.
And then
I'll do that, but then I realized I need to update that preprint to arXiv too.
And then Peter just texted me. Is it Peter or Petar?
It's Petar.
It's Petar.
We are. I think we're from the same country, as far as I know.
Are you Croatian?
Yeah.
You know, I was guessing a little bit. Where did you grow up?
I grew up in Herzegovina. I'm
Oh,
from,
okay. Further down.
But yeah, further down. But yeah, I did my bachelor's in Zagreb.
You know, there is a very famous bevanda, of course, where I grew up, which is in Rijeka.
Okay.
But very different profile. He was a big very famous motorcycle racer, and actually ended up having few Michelin star restaurants in the area. So, so I knew the name from there, and I guessed it might have, you know, it might be. So Petar, yes, that's the correct paper, the functional spaces paper.
Yeah, but I was actually, we made this construction completely with the notion of knowing that basically these monomials are closed for linear systems. And we just basically modulated or morphed these monomials to fit our nonlinear dissipative system, which is kind of pretty crazy.
That is remarkable. So wait,
that's basically mentioned where you mentioned we basically made a tailor-made Fock space for dissipative systems.
Okay, well, that's you know, well, so it seems like you've discovered, you know, the kind of stuff that I was talking about in that paper, right? In 19.
Yeah, but completely from the other way around, we kind of considered aggregation of nonlinear systems. But yeah, the interesting thing is this dissipative system, what we tested it out was actually a stochastic data set, and we fitted a deterministic model that's incredibly robust, and the prediction spans over 3 to 8 seconds, and we have an LTI system that predicts basically pretty surprisingly well fits the dissipative system, the nonlinear dissipative system.
Okay, that's actually remarkable. I actually did notice that paper, and here is an invitation. So I think I'm going to make this a bit of a, you know, constant, maybe not every week, but I like different groups around the world. There is a lot of work, and I think there is not enough work on the type of topics that we heard today. You know, out of 84,000 references, I can bet you that, you know, 83,900 basically use the methodology to look at some spectra of something and then extract value. Now, they extract value. So it's interesting, right? Because they're clearly getting some value from what they're computing. But my heart was always in trying to formulate a rigorous mathematical setup for computation. And this was clearly the talk in which, we're doing this. So Petar, you're next. But let's do it after. Could you give a talk like this after the new year?
Yeah, I think I'd be more than happy.